In this video, we begin to look at some of the biological applications of what I'm going to call pseudo-acyl transfer reactions. And we're going to start looking at phosphate esters and specifically at ATP and how the body hydrolyzes ATP. Recall that we have previously discussed the hydrolysis of regular esters and the hydrolysis of amides. So before I could talk any further about phosphate esters or ATP, we have to talk a little bit about phosphoric acid, because you may not always be carrying the chemistry of phosphoric acid in your back pocket with you. So phosphoric acid is a triprotic acid. So it's got a P double bond O and 3 OH groups on it. And the triprotic acid is, of course, going to have 3 different pKa values. So phosphoric acid is not a strong acid in the classic definition, in that it does not have a negative pKa for the removal of its first hydrogen. The first pKa value is 2.15, so it is still technically a weak acid, which means that equilibrium constant is going to be less than 1. But in the realm of weak acids, 2.15 is a fairly strong weak acid. Okay, so that would give you the monoanion. Then for deprotonating the monoanion to give a dianion, the second pKa is 7.21. And then for deprotonating the dianion to give a trianion, the third pKa is 12.35. So what you need to be aware of is that at physiological pH, phosphoric acid, physiological pH of course is pH 7.4, phosphoric acid is going to exist as a mixture of the monoanion and the dianion. Because recall from the Henderson-Hasselbalch equation, when the pH is equal to the pKa, which is approximately true here, physiological pH is approximately the same as the pKa, second pKa. So when the pH equals the pKa, the concentration of acid and anion are going to be equivalent. So that's why we're going to have a mixture of the monoanion and the dianion. So a phosphate ester is simply when we replace the hydrogen, any number of the hydrogens of phosphoric acid, 1, 2, or 3 of them, with R groups. And then we also need to be aware of what a phosphoric anhydride is. And that's when the R group is another phosphorus atom that's also doubly bonded to an oxygen. All right, so now I want to introduce you to our friend ATP. So ATP stands for adenosine triphosphate. So what that means is we've got an adenine ring up here. This is an example of an aromatic heterocycle. So this ring system that has the 4 nitrogens in it is an aromatic ring. It's a purine ring. And it, of course, is the same adenine that exists in the adenine of DNA. The adenine is linked to the sugar ribose, which is a 5-carbon sugar, which exists in its cyclic form. And so the cyclic form has a 5-membered ring with 4 carbons and an oxygen in the ring. And then the 5th carbon is sticking up out of the left-hand side of the ring, and that is bound to an oxygen, which is bound to a phosphorus. So there you have the phosphate ester moiety, and then that first phosphorus is bound to an oxygen, which is bound to a second phosphorus. Thus you have an anhydride linkage, and then that second phosphorus is bound to an oxygen, which is bound to a third phosphorus. So you have another phosphoric anhydride linkage. So ATP is actually a combination of a phosphate ester and a phosphoric anhydride. At physiological pH, the most prevalent form is going to be the tetraanion of ATP, which means it's going to have 4 negative charges. Each of the closer to what I'll call the proximal phosphorus atoms have one negative charge, and then the terminal phosphorus atom has an oxygen with two negative charges. All right, so ATP is nature's energy storage molecule, and the way that you get out that stored energy is by hydrolyzing ATP, which means that the hydrolysis reaction is exothermic, and the amount of energy that is released in the hydrolysis reaction is 30.5 kilojoules per mole. So what you have probably all seen in a biology course, assuming you've taken some course involving cellular biology at some point in your life before watching this video, is the following equation. ATP plus water, or they may not even put the plus water in there, but if it's a hydrolysis you need water, becomes ADP plus PI. And you've seen this, you know you get energy out of this, and you probably have no idea exactly what these molecules look like or exactly how this reaction happens. So that's what I would actually like to cover in this slide. Okay, so the mechanism of hydrolysis, there's a lot of stuff going on this slide. What I've done is I've actually taken ATP and flipped it over, so the terminal phosphate is now on the right side, and the adenine and the ribose do not get involved in this mechanism. So I've taken the liberty, as much as biologists may not like this, to abbreviate all that by R. So I've drawn out the three phosphates because that's where the business of the hydrolysis reaction happens. Okay, so in the first step, water is going to attack the terminal phosphate. Because remember, what we have to get out at the end of this is ADP, which is labeled at the bottom, and PI. So there are two phosphates that still have to be bound to the adenine and the ribose. Therefore, it is only the terminal phosphate that's going to come off in this hydrolysis reaction. So what I've got going on in the first step here is I have water coming in and attacking this first phosphorus to give you what I've told you over and over again you can't have: an oxygen with a positive charge and an oxygen with a negative charge in the same molecule. Well, now I'm going to plead the fifth, so to speak, and say this step requires enzymatic catalysis. That is fundamentally what enzymes can do. They can take intermediates that would otherwise be unfavorable and lower the energy of those intermediates, and in lowering the energy of the intermediate, it lowers the activation energy required to get to that intermediate. Okay, so a positively charged amino acid will come in close contact with the developing negative charge when water adds, and then a negatively charged amino acid will come in close contact with the hydrogens of the water that added nucleophilically. So again, enzymes allow something that would not be possible otherwise in the laboratory. And not only do they allow them, you have to remember they have to allow them to happen at pH 7.4, at neutral physiological pH. So it doesn't make sense. I could draw a mechanism under strongly acidic conditions. I can draw a mechanism under strongly basic conditions. We have seen these mechanisms already. Just substitute the phosphorus for a carbon. But in the body, you don't have strongly acidic conditions, and you don't have strongly basic conditions. So we have to use enzymes to help us out and make the reaction happen under essentially neutral conditions. Okay, so once we've gotten to this first intermediate, which the enzyme has to help out with, the rest of it is downhill. Okay, so the next step is going to be a proton transfer reaction from the negatively charged oxygen is going to go grab the proton that is on the positively charged oxygen, and you're going to end up with two OHs that are neutral. Okay, that's going to be a very favorable step. And then finally, you're going to complete your acyl transfer mechanism by taking your intermediate. I can't call it a tetrahedral intermediate because phosphorus is actually forming 5 bonds, rather than carbon, which forms 4 bonds. But what I will call this instead is the trigonal bipyramidal intermediate, because that is the geometry about phosphorus. You will take the trigonal bipyramidal intermediate, reform the PO double bond, and kick off ADP, which is ultimately what you want as a leaving group. So the driving force behind this reaction is actually the separation of charge. You are starting with something that has 4 negative charges in close proximity and breaking it apart into 2 molecules, one of which, ADP, has only 3 negative charges, and the other one, phosphate, is going to have 1 negative charge. Okay, so this is how the body hydrolyzes ATP. Then the other important application of phosphate esters is in terms of forming phosphodiester bonds in the backbone of DNA and RNA. And we will consider that in the next video.